Section 1 Introduction. In this paper, we delve into the fascinating world of transformers and large language models, LLMs, which are known for their ability to adapt and learn based on the data provided to them. Recent studies have shown that these models can solve tasks with limited examples by learning from the data in the context. This learning process is similar to how gradient-based optimizers work. However, it's not clear if these findings apply to models trained on sequential data, which is the common training setup for LLMs. To address this, we build on existing theories and demonstrate that transformers trained on sequence modeling tasks can predict using gradient descent learning based on in-context data. This means that when a transformer minimizes a generic autoregressive loss, it triggers a secondary gradient-based optimization algorithm within the transformer's forward pass. This process is known as mesa-optimization. We also found that these mesa-optimization algorithms can learn from a few examples in the context, regardless of the model's size. This supports previous findings about the emergence of few-shot learning in large-scale LLMs. Our contributions include: 1. We expand on existing theories and show that transformers can predict the next element in a sequence by optimizing internally constructed objectives using gradient-based methods. 2. We reverse engineer transformers trained on simple sequence modeling tasks and find that their forward pass implements a two-step algorithm. First, early self-attention layers group and copy tokens to create internal training datasets and define internal objective functions. Second, deeper layers optimize these objectives to generate predictions. 3. We show that these simple models trained on autoregressive tasks become in-context learners, and that prompt tuning, which is essential for improving in-context learning in LLMs, also improves performance in our setting. 4. We introduce the mesa layer, a new attention layer that efficiently solves a least squares optimization problem, instead of taking just a single gradient step towards an optimum. We show that a single mesa layer outperforms deep linear and softmax self-attention transformers on simple sequential tasks while offering more interpretability. 5. We conduct preliminary language modeling experiments replacing standard self-attention layers with the mesa layer, and obtain promising results demonstrating strong in-context learning capabilities enabled by the layer. We also study causally masked, autoregressive transformers where self-attention is the fundamental building block. Given a sequence of T input tokens, a self-attention layer with H heads and parameters theta updates the current token as follows. It calculates a query for each head, and then uses this query to calculate an attention vector. This attention vector is then used to update the current token. We also consider linear attention models, which simply omit the softmax nonlinearity. These models use a weight matrix that doesn't scale with time but encodes information from all past tokens, allowing inference at constant memory cost. This is why linear attention is currently of great interest. Section Summary. In this section, the authors explore how transformers trained on sequential data can predict using gradient descent learning based on in-context data. They demonstrate that minimizing an autoregressive loss leads to a subsidiary gradient-based optimization algorithm running inside the forward pass of a transformer. They also introduce a novel attention layer called the mesa layer, which outperforms standard self-attention layers on sequential tasks while offering more interpretability. Section. Linear self-attention can implement one step of gradient descent. In this paper, we delve into the concept of linear self-attention and its ability to perform a single step of gradient descent. This idea was initially proposed by previous researchers who demonstrated that a single attention layer could perform one step of gradient descent on a quadratic cost function, using in-context data. This implies that multi-layer transformers could theoretically reduce the loss to any desired level through multiple steps of gradient descent. We aim to extend this concept to the autoregressive setting in this paper. Let's start by revisiting the original model and task setting. The objective is to meta-learn the parameters of a linear self-attention layer, enabling it to solve supervised learning tasks. Each task is defined in context by a training set and a test input. The goal of meta-learning is to minimize the difference between the correct output and the actual output of the linear self-attention layer, averaged over a distribution of linear regression tasks. A common approach to solve a linear regression task is to use a linear model with parameters learned by gradient descent on the squared error loss. Starting from an initial parameter, a gradient descent learner updates it by taking a step along the negative of the gradient. The main finding of the previous research is a theoretical construction showing that a linear self-attention layer can perform exactly one such gradient descent step. To illustrate this, we construct a set of tokens, including a query token not contained within the training set, where we place the test input for which a prediction should be made. Under this token construction, if certain conditions are met, the query token, after one such layer, contains the prediction obtained by a linear model that underwent one step of gradient descent. Therefore, this self-attention layer implicitly constructs a least squares optimization problem and takes one step of gradient descent towards solving it. This layer can be stacked to implement multiple steps of gradient descent. We then move on to the concept of sequential prediction by least squares mesa-optimization. The construction reviewed above is designed to solve few-shot supervised learning problems. However, when we move to a general autoregressive modeling setting, the approach changes slightly. Instead of asking whether an attention layer can solve few-shot supervised learning problems that are presented in context, we ask whether transformers can rely on mesa gradient descent to predict future inputs. In this case, a self-attention layer has to learn sequentially as some inputs are gradually unveiled. The goal at each time step is to minimize the autoregressive loss. As in the previous section, we assume that the model always starts from the same initial weights, and that learning corresponds to taking only a single gradient step. To adapt to the autoregressive setting, we modify the token construction to include an additional separate first channel to be filled with the prediction of future inputs at every time step, alongside channels for the previous and current sequence element. By providing neighboring elements within one token, self-attention is able to compute dot products of targets and inputs of the loss necessary to compute the gradient. Then, to update the first channel of such a token with the prediction of a linear model learned with one step of gradient descent, it suffices to set certain conditions. We refer to this result as the one-step mesa gradient descent construction. Section summary. Linear self-attention layers in transformers can implement one step of gradient descent, allowing them to minimize the loss of a quadratic cost function on in-context data. This result has been extended to the autoregressive setting, where the goal is to sequentially predict future inputs by minimizing the autoregressive loss using mesa gradient descent. The self-attention layer constructs a three-channel code to include the prediction of future inputs, and by updating the first channel with the prediction of a linear model learned through one step of gradient descent, it effectively performs mesa gradient descent. Section. Multi-layer mesa-optimizers. Let's delve into the concept of multi-layer mesa-optimizers, which are used in deep networks made up of stacked linear self-attention layers. It's tempting to think that each layer simply performs a step of mesa gradient descent, similar to the process used in few-shot learning. However, this might be an oversimplification when it comes to trained autoregressive transformers. The first clue that this might be too simplistic is that stacking the one-step mesa gradient descent over multiple layers doesn't result in the standard gradient descent. Instead, we end up with an unusual online gradient-based optimizer, which is expected to perform worse than the standard gradient descent. This finding, along with a mathematical analysis of the resulting optimization algorithm, is discussed in a study that highlights the drawbacks of causally masked attention for few-shot and context learning. This leads us to question whether transformers can implement more efficient mesa-optimizers. We propose an alternative mesa-optimizer that also uses causally masked self-attention layers. This new optimizer works in two stages. In the first stage, one or more self-attention layers are used to implement an iterative preconditioning procedure. This results in a regularized mesa objective with an improved condition number compared to the original objective. Here, we have a preconditioning matrix and a scalar that controls the regularization strength. This preconditioning procedure has a unique property. Under certain conditions, as the number of layers increases, the preconditioning matrix converges to a specific value. This value is the inverse of the sum of the product of the data matrix and its transpose, plus a scalar times the identity matrix. The data matrix's columns are the input data. In the second stage, a final self-attention layer takes a single gradient descent step on the preconditioned mesa objective. This two-stage algorithm is theoretically sound. When the preconditioning matrix equals its converged value, the regression problem is solved in a single step, starting from zero weight initialization. We provide a simple weight and input token construction to implement this algorithm in the appendix. Our new construction uses the truncated Newman series to iteratively approximate the required inverse matrix vector products in parallel for all time steps, without ever explicitly representing any of the preconditioning matrices. In the next section, we assume that mesa-optimization is a desirable feature for a model to have. We discuss a modification to the architecture that makes this behavior a default feature within a transformer. We introduce the mesa layer, a novel self-attention layer that fully solves a layer-specific optimization problem, instead of only descending a loss function with a single gradient step. This layer is closely related to the delta net model, which is hardwired to do one gradient descent step per time point. We focus on causally masked autoregressive problems, while noting that the insights remain the same for other strategies such as BERT-style masking. Given a sequence of tokens, we design a layer that changes the tokens following an update. This update is the sum of the product of a projection matrix, a mesa-optimizer weight, and a query vector for each head. The mesa-optimizer weight minimizes a regularized sum of the squared differences between value vectors and the product of the weight and key vectors, plus a regularized sum of the squared Frobenius norm of the weight. The value vectors specify targets to which an internal model with parameters should map training and test inputs, represented by keys and queries, respectively. The minimizer of a regularized version of the objective can be immediately mapped to the update under the token construction discussed in the previous section by appropriately setting the projection matrices. At any given time step, computing the update requires solving a regularized least squares problem per head. To efficiently solve this sequence of optimization problems, we leverage the recursive dependency of the solutions of these consecutive problems, which can be expressed in closed form. We now use a formula to obtain the inverse at time t from the inverse at the previous time step t1. This iterative update is possible because we only change the inverse by a rank 1 update. This solution scheme is known as recursive least squares. With this, we can compute the update, which requires 2 additional vector matrix and 2 vector-vector multiplications per step compared to the standard self-attention operation. Note that since our intermediates consist of matrices of dimension across the time steps, naive backward gradient computation requires storing them in memory. Fortunately, this memory overhead can be avoided using the Sherman-Morrison formula in reverse during the backward pass, enabling memory-efficient gradient computation of the output of the mesa layer with respect to its inputs. We further note that while the implementation described here has a desirable constant inference memory cost like standard linear self-attention, it is not parallelizable across time during training. This is a disadvantage for training on contemporary hardware shared with recurrent neural networks, but not with standard softmax or linear self-attention. As discussed in the appendix, in practice this significantly slows down our experiments. We demonstrate the expressivity and performance of the mesa layer in reverse engineerable sequence learning tasks as well as in language modeling in the next sections. Section Summary. The section discusses the concept of multi-layer mesa-optimizers in deep networks, specifically autoregressive transformers. It highlights the limitations of stacking one-step mesa gradient descent constructions and proposes an alternative mesa-optimizer that operates in 2 stages, iterative preconditioning and a final self-attention layer. The section also introduces the mesa layer, a self-attention layer that fully solves a layer-specific optimization problem, and explains its role in mapping training and test inputs. Section 5.1 Prediction of linear dynamics by in-context learning. In this section, we aim to understand how transformers, trained on simple synthetic autoregressive tasks, predict linear dynamics. We have 2 main objectives. Firstly, we want to see if these transformers use mesa-optimization algorithms to predict future inputs. Secondly, we want to find out if adding a mesa layer can enhance the performance of standard transformers by replacing multiple attention layers. We focus on fully observed linear dynamical systems. To create a sequence, we first draw a random weight matrix and a random initial state. Subsequent states are then generated according to a rule that introduces Gaussian noise. We use a random orthogonal matrix for the weight matrix, which we found to be important as converging linear dynamics led to different inference algorithms. This approach prevents the memorization of the weight matrix and simulates the diversity present in real-world data. To predict future states from a given past sequence, we typically use a linear model where the weights are learned by minimizing a certain loss function, possibly with an added regularizer. We then analyze various configurations of transformers trained through stochastic online minimization of the autoregressive loss. This loss function measures the difference between the actual future state and the predicted future state. The transformer model uses the current state as a query and the past sequence as context. We refer to the minimization of this loss function as the base optimization process. To measure in-context learning performance, we monitor the evolution of the per-time step loss as a function of context size. This allows us to see how the prediction of future inputs improves as more context is provided to the model. Our hypothesis is that base optimization gives rise to a mesa-optimization process responsible for generating predictions. Specifically, for our linear generative model, we believe that learning results in transformers that predict future inputs by representing a linear model with mesa parameters, constructing the least squares mesa objective using in-context data, learning the mesa parameters by minimizing the mesa objective, and applying these parameters to predict the next state. We start by testing our hypothesis on single-layer transformers that only use linear attention. We believe that providing the transformer with input target pairs encourages mesa gradient descent. We then train the transformer by online mini-batch gradient descent, generating new sequences at each base optimization step. We are able to perfectly identify the algorithm that this single-layer transformer uses to generate predictions. We confirm that the layer is indeed implementing a step of mesa gradient descent by comparing the loss reached by the trained layer with a linear autoregressive model learned through one step of gradient descent. Interestingly, we find that the learned one-step algorithm is still significantly outperformed by a single mesa layer. This suggests that hard-coded inductive biases in favor of mesa optimization can be advantageous. Section summary. In this section, the authors aim to understand whether auto-regressively trained transformers use mesa optimization algorithms to predict future inputs. They analyze various configurations of transformers trained through stochastic online minimization of the autoregressive loss and propose a hypothesis that learning yields transformers that predict future inputs by implicitly representing a linear model with mesa parameters and constructing a least squares mesa objective using in-context data. They verify their hypothesis on single-layer, linear attention-only transformers and find that the resulting learned one-step algorithm is still outperformed by a single mesa layer. Section. Multiple self-attention layers. Let's delve into the world of multiple self-attention layers. We've gained some theoretical insights from our previous work on multi-layer models, and now we're ready to explore deep linear and softmax attention-only transformers. We've designed our inputs in a way that allows us to implement both multi-step mesa optimization and our iterative preconditioning algorithm. This design also enables us to mix both methods. Just like with single-layer models, we can see a clear structure in the weights of the trained models. We've developed an algorithm, which we call rev-alg-d, that uses only 16 parameters per layer head, instead of the usual 3,200. This algorithm, although complex, can accurately describe a trained model. It even allows us to transition between actual transformer and rev-alg-d weights almost seamlessly. However, interpreting the rev-alg-d expression as a mesa optimization algorithm is challenging. So, we've turned to a linear regression probing analysis to look for signs of our hypothesized mesa optimization algorithms. We're looking for evidence of two things: a stacked multi-layer gradient descent construction, and our new iterative preconditioning algorithm. Our analysis involves using two targets for regression: the future state to be predicted, and the preconditioned current input. The latter allows us to solve the least squares problem in a single gradient descent step. Our findings show that both targets can be linearly decoded, with decoding performance improving with sequence length and network depth. This suggests that base optimization has discovered a hybrid algorithm that improves the condition number of the mesa optimization problem while descending over layers the original mesa objective. We also found that performance improves significantly with depth, with a 6-layer model coming close to, but not quite matching, a single mesa layer. These results support our hypothesis that a fast descent on the autoregressive mesa objective is achieved through mesa optimization on progressively better preconditioned data. Now, let's move on to full-fledged transformers. We've relaxed all previous architectural simplifications and trained standard transformers that use positional encodings, input and output projections, and process raw tokens. We believe that after autoregressive training, these models operate in two stages. First, they use positional information to recreate our token construction in the first softmax self-attention layer through a copying mechanism. This essentially sets up an internal mesa-optimization problem. The second stage involves implementing a mesa-optimizer that solves the self-constructed least squares problem. We've used our two candidate constructions, mesa gradient descent steps and iterative preconditioning, to guide our analyses. We compared three model families: softmax-only transformers, and hybrid models that have a first softmax layer followed by either linear or mesa layers. We found that transformers of all three types learn copy layers when trained on linear dynamics. We then examined the post-copying behavior of the models. Although we could see some interpretable identity structure in the weight matrix products of the transformers, we believe that the initial embedding layer introduces too much ambiguity on how the input data is represented and processed by the subsequent attention layers. So, we used the same simple linear regression analysis to probe hidden layer activations. We found that hidden activations gradually become more predictive for both the target and the inverse probes. Interestingly, we observed a hard transition-like behavior at the last layer in terms of target decoder performance. In conclusion, our findings suggest that deep transformers trained auto-regressively on simple linear dynamics implement prediction algorithms based on mesa-optimization principles. These iterative algorithms allow a standard transformer to almost match the performance of a learned mesa layer, which achieves optimality for the task considered here. Section summary. The authors analyze deep linear and softmax attention-only transformers and find that a compressed algorithm can describe a trained model, allowing for interpolation between actual transformer and compressed weights. They also use linear regression probing analysis to look for evidence of their hypothesized mesa-optimization algorithms and find that both target and inverse probes can be linearly decoded, with decoding performance increasing with sequence length and network depth. Additionally, they relax architectural simplifications and train standard transformers that use positional encodings, input and output projections, and find evidence that these models operate in two stages: a copying mechanism in the first softmax self-attention layer and subsequent layers implementing a mesa-optimizer that solves the self-constructed least squares problem. Section 5.2 Simple autoregressive models become few-shot learners. In the previous section, we discovered a strong link between transformers trained using autoregressive methods and gradient-based mesa-optimization. This naturally leads us to question whether these models can be adapted to learn in context when given a small amount of regression data. We explored this question by altering the sequence generation after training from a linear dynamical system to a linear regression task. To create our few-shot tasks, we continued to use a randomly sampled orthogonal matrix as the ground truth, just as we did during training. However, we now used this ground truth model to generate a labeled training set with inputs and targets. We then presented this dataset to our transformers, which had been trained using autoregressive methods, as a sequence of tokens. As the sequence progressed and more training data was presented, we measured in-context learning performance through the mean squared error between the transformer's output and the corresponding target. It's important to note that both the sequence generative model and loss function are different from the ones used during training. Despite this, we found that the transformers were capable of few-shot learning. Even though they were never trained in this setting, we observed that the transformer's loss decreased with sequence length. This indicates that the model can learn in context, using additional in-context training data to improve its predictions. As a control, we also reported the performance reached by the least squares solution obtained on the dataset, and observed a similar decrease in loss. This dataset, where half of the associations consist of incorrect input-output pairs, corresponds to the training set an autoregressive transformer learns from. In this sense, our models achieve a few-shot learning performance that is not far from optimal. Our results show that training transformers on simple autoregressive tasks can lead to in-context few-shot learning. To further improve the in-context learned predictions, we fine-tuned a single token, which we refer to as the EOS token. This technique, known as prompt or prefix tuning, has been shown to significantly improve performance when applied to large language models. Finally, we demonstrated that our trained transformers can learn multiple tasks in a row. We studied the minimal setup where the model has to learn two tasks, generated from two distinct ground truth linear models. We found that the trained transformer has the capability to overwrite the first and learn a second task in context, even though it was never explicitly trained to solve such sequential learning problems. Section Summary. In this section, the authors investigate whether autoregressively trained transformers can be repurposed for few-shot regression tasks. They find that these models can learn in context when presented with few-shot data, improving their predictions as more training data is provided. Prompt tuning, where a single token is fine-tuned, and the use of prefix prompts further enhance the few-shot learning performance. Additionally, the trained transformers demonstrate the ability to learn multiple tasks in a row, even though they were not explicitly trained for sequential learning. Section. A toy model for in-context learning. Let's delve into a simplified model for in-context learning. We've found that transformers, which are trained to predict the next element in a sequence, can be easily adapted for in-context learning. This is due to the similarity of the algorithms they use. This opens up a controlled environment for us to explore interesting aspects of in-context learning, such as the benefits of prompt tuning and the ability to learn continually. These simplified models could be a useful platform for future research into the strengths and weaknesses of in-context learning as seen in large language models. Now, let's shift our focus to language models equipped with least squares solvers. Transformers have brought about a revolution in autoregressive language modeling. However, it's challenging to reverse engineer these models to the same extent as our previous analyses. So, we base our conclusions on performance comparisons between standard transformers and new versions that incorporate a mesa layer. We hypothesize that this mesa layer will enhance the in-context learning and working memory capabilities of a transformer, especially the linear kind. We also believe that this will lead to improvements in language modeling, given the strong correlation between in-context learning and actual autoregressive loss. We measure performance in two ways: the next token prediction loss, which is the actual goal of base optimization, and the ability to learn in context, which we measure as the difference in loss calculated at 2 points within a sequence. We train transformers with various architectural configurations on the pile, a large collection of various English text datasets, including parts of Wikipedia, archive, and code. We always model the first layer using softmax self-attention in all experiments. This decision is based on insights from our previous experiments, where base optimization consistently attributed a mesa objective creation role to this layer. We then compare pure softmax-only transformers to two types of hybrid models, where the subsequent layers are either linear or mesa. We vary the depth of our models, from 2-layer attention only to deeper 4-attention layer models with token-wise MLPs, which are standard in transformers. By transforming the data nonlinearly, MLP layers allow solving nonlinear regression problems by mesa gradient descent. We also adopt in our hybrid linear and hybrid mesa transformers a deterministic parameter-free projection, a simple-to-compute nonlinear transformation of keys and queries. We found that this significantly improved the performance of non-softmax attention layers. To represent discrete input symbols as real-valued vectors, we learn a vocabulary of real-valued vectors using the standard GPT-2 tokenizer. All architectural and training details can be found in the appendix. We note that all models have an almost identical number of parameters. In line with our synthetic experiments, we observe stable learning across all model types of copying layers, indicated by the constant attention to tokens in direct or close proximity. This phenomenon is predicted by the mesa-optimization theory presented here, where copy layers serve the purpose of constructing internal mesa objective functions. We note that, unlike our previous synthetic linear prediction tasks, the pile is no longer Markovian of order 1. This is reflected in the more complicated attention maps, indicating more involved copying behavior. We also run a comparison where we compare to a single-layer control model whose first softmax layer is removed and replaced by a hard-coded one-step key shift operator. Interestingly, such an operator can be found in previous work. Again, we verify the findings of strong in-context learning scores within a single layer, with the mesa layer performing on par with softmax. As in previous experiments, deterministic parameter-free projection features substantially improve performance. We fix the size of this feature to 3 for the linear as well as the mesa layer for all other language modeling experiments. We find that the hybrid mesa transformers outperform their hybrid linear counterparts in terms of performance, across all configurations, essentially matching or coming closer to pure softmax transformers. We leave for future work studying the mesa layer equipped with forgetting factors, which could further improve upon our results here. This is reflected both in terms of perplexity and in context learning scores. Strictly speaking, these results are not sufficient to make claims on whether mesa optimization is occurring within standard transformers. However, the high performance achieved by the hybrid mesa models, which operate on mesa optimization principles by design, suggests that mesa optimization might be happening within conventional transformers. More reverse engineering work is needed to add weight to this conjecture.